Good morning or good afternoon, ladies and gentlemen. Here we are with the first lecture of the coronavirus quarantine school year or school semester. Right, what we're going to do today is going to review for the exam. This is some material that you already covered, you already had before spring break, before all this mess happened. And we're just going to review what we're going to be on the test. And looks like we're just going to have a take-home test, bunch of problems, maybe some short answer questions, open book, open note, open resource, whatever you want to do. And we'll show how you work on these things in a few minutes. So what we're going to do is, I want to point out, you actually worked on this. I'm going to say right now we're not going to do a multiple choice test. We're actually going to just do a written test. It's going to be short answer problems, open note, open resource, basically anything that you find. The test is going to look a little bit different, not as much. It may have some owl problems, but usually this is going to be ones I've written, and we're going to cover some of those what we're going to cover. Each test will be unique. It's going to be over the same material, but if somebody has aluminum silver chloride, we'll use silver iodine or something else. That it will be, you'll solve it similarly, but different numbers, different compounds. All right, so here are the main topics, other than the stuff that we talked about in lecture, but these would say about 80% of the stuff we're going to cover. Gas and water equilibrium, solid and water, KSP, chemical reactions, dissolving dissociation with the solid and water, and then looking at chemical reactions, how we work with this. So we'll go look at Henry's law. So let's look at Henry's law for a second. Now, Henry's law is basically, we're looking at, and let me get my pen over here. Well, there we are. So KSP, K is equal to concentration of a gas. So X is an unknown gas, and we're going to have it over the pressure of this unknown gas. So this is Henry's law. So Henry's law is basically a gas dissolving in a liquid, say some type of gas, and it's going to be inside a liquid, and afterwards we have it dissolved. And this is a constant. So all these are going to have a certain constant, certain number that it will be the same. So if you look at this, so if you look at, say we have 0.0050 as our Henry's law constant, and we have, say, 0.25 atmospheres of pressure. Make sure you convert all your pressures to atmospheres. That's something I keep forgetting, and that's easy to forget, to be honest, is that pressure has to be in atmospheres, because that is how all these equilibrium constants are used in. So the unit of this is 0.0050 mole per atmosphere, moles per liter per atmosphere, or molarity. So to solve this, you got K is equal to the concentration of X over the pressure. Multiply both sides by pressure, so you basically got pressure times K is equal to the concentration of X, and this is where you use your handy dandy calculator. You may have mine, you got your phone, you use whatever calculator you like to use with this. And imagine me saying that to you guys. So 0.005 times 0.25, and you're going to get this concentration of X is equal to 0.00125, and that's going to be molarity. And you notice I'm running out of space. Move that over, and there we go. And so that's how you solve these problems. Now, here's the thing is that what is concentration? Remember, the concentration units can be in molarity, which is moles per liter, but we also going to have it in grams per liter, or something per liter. So concentration can be anything, any unit that's related to mass or amount per liter. Now, with this problem here, we have 2.6 grams of a gas in 2 liters of liquid at pressure 1 atmosphere. And so what we want to know what the mass of the gas that's dissolved in these 2 liquids when we increase the pressure to 5.5. So if we come over here, So 2.6, the concentration of 2.6 grams per 2 liter. That's equal to our concentration. So so we have a concentration and we've got pressure. P is equal to 1 atmosphere. Now I'm going to point out, so with this, we've got this equation that the constant is equal to the concentration over pressure. This number stays the same no matter what. The constant temperature, this remains the same, and x is over P. So if we have, therefore, this is what these three triangles mean. Therefore, x at 1, pressure at 1 is equal to x at 2, pressure at 2. So we come down here, we got x at 1, which is 1.3 grams per liter, over pressure 1 is 1 atmosphere. And that's equal to what we don't know, over 5.5. So we want to know what x is. Now remember, how do we get this 1.3? That's 2.6 divided by 2. So use a calculator. X is going to be equal to, let me open my phone up, calculator. So 1.3 times 5.5, that's going to be 7.15. That's going to be that's the concentration. That's grams per liter. Now, we have 2 liters. So take this times 2. So the amount is going to be 14.3. That's my answer for this. It's going to be 14.3. This is my answer. Why? Remember, if I could spell, volume is equal to 2 liters, but the concentration is in grams per 1 liter. So whatever we get the concentration, times it by 2, which reflects 2 liters of our solution. That's why I multiply by 2. All right, let's go to the next question. Balancing equations and equilibrium. This is something we did. I actually asked you guys to do. And what I want you to do is provide the balance equilibrium and equilibrium expression. So go back here, come to this next slide. So sodium carbonate. So that you need to look up on, say, let's go to here. Voila. And so what we look for is formula of sodium carbonate, and oh look, Na2CO3. So now you got to figure out what this actually looks like. And if you look over here to where it says sodium carbonate on the right, Na2 lowercase 2 CO3. So there's my and you got some other information there, but we just need the formula right now. So we have the sodium carbonate. So up here is Na2CO3, and we're adding, whoops, let's stop that. Let me redo this. I must have pressed something I shouldn't have. All right, let's go sodium carbonate, Na2CO3, and we'll add that to iron nitrate. Iron 3 nitrate. So iron 3 nitrate is Fe, parentheses, NO3, 3. Okay, now we need to balance this equation. So this is what we call double displacement, where these two, this and this will switch. And we need to figure out what is precipitate and what is going to be the resulting salts. So what we can do is we can use the net ionic equation. We'll just look at this and say, okay, NO3, 3, so that we know we're going to have Na positive in solution. And we got 2 of those. and we're going to have CO3 minus 2. And we just got one of those at the moment. And plus we got one iron. That's a plus 3. And we got 3 NO3 minuses. Now what's going to happen is that these two are going to combine. And that's going to that'll be iron carbonate. Now iron carbonate, iron 3 carbonate, if you look that up. Okay, let's look this up for you guys. Come back down here. So come up here and formula, and we're going to say replace the sodium with iron 3 carbonate, and oh look, there we go, Fa2CO3. And this is actually fairly insoluble, so this is going to be our solid. So if we come back to here, whoops, let me make this go down. So our compound is going to be Fe2. Stop that. Let me erase this again. Sorry, folks. Keep hitting the wrong button. So this is going to be Fe2, CO3, and that's going to be a parentheses, 3. All right, and then we're going to have NaNO3. We need to figure out what that coefficient is. Now, so let's rewrite this down here. We're going to rewrite this again. So we have something Na2CO3 plus FeNO3 3, and that will yield NaNO3 plus I think I know what's happening. You guys get to see and laugh at me because of my control of this program. And that's going to stop. I'm going to keep pressing the wrong button here. This pen's driving me nuts. So that's going to be Fe2CO3 3. Now here we go. So let's balance NaCO, and then we got some more O's. We have nitrogen and we have iron, Fe. So on the left-hand side, we got 2 irons, 1 carbon. Let's go to 1 iron, and then we have 3 nitrogens, and then 3 times 3 is 9, plus another 3. That's going to be 12 oxygens. Now remember, these guys really don't break apart. So they could be actually a unit. So we could say CO3 and NO3. On the right-hand side, we have 1 sodium, 1 nitrogen, 2 irons, 3 carbons, and we got 3, 10, that's 9, plus another 3, that's 12 oxygens. Well, this is all going to change. So let's take a look at how these things are going to change. So we're going to pick the heaviest element, and that's going to be iron, our friend iron. So we've got 2 on the right, 1 on the left. Let's add 2 over here. So that makes that 2 ions. And now we're going to have to change the number of nitrates. So that's going to be 2 nitrogens on 2 times 3, that's going to be 6. And we got 1821 oxygens, because if you look over here, we have each iron nitrate has 9 oxygens to begin with. Now we've got 2 units. That's going to give us 2 times 9 is 18, plus 3 more, that's going to be 21. So now we balance the iron. Let's go to the sodium. We got 2 over on the left. We need 2 on the right. But if we do that, so we need 2 on the right. So that gives us 2. Carbon, we still have 1 here. 3 still, nope. Oxygen, we're adding 3 more to this mix. So that gives us 15. Nitrogen is now to 2. And iron is 2. It's still balanced. Sodium is balanced. Now let's look at nitrogens next. We need to multiply nitrogen by 3. So we got 2 already. We need 6. So if we change this to a 6, multiply that by 3. Now we got 3 nitrogens. 6 nitrogens what we need. Now we got 6 sodiums. And now we got 18 and 18. That's going to be a lot of oxygens. That's going to be 36. Now let's go back up to sodium. Now we got 6 on the right, 2 on the left. So you need to multiply this one by 3. Now this is where it comes into clear. Now 3 times 2 is 6. 3 carbons now changes to 3 because we've got 3 of them now. And if you take a look at count all the oxygens, 3 times 3 is 9. Plus again our, whoops, and I should take that. Yeah, that's right. 9, and then that should give us our I gotta make sure I count this right. I got 30. 3 times 3 is 9 plus 18. That's going to be 27. Did I count this right? 3 times, that's 18. 3 times 3 is 9 times 2. That's 18. That's going to be 36. 3 times 3 is 9. 3 times 3 is 9 times 2 is 18. And Dr. Bailey can't add with a crap, can he? But the thing is, this should be balanced. Oh, let's try this again. 3 times 6 is 18. Oh, 18 plus 9 is 27. There we go. Everything's balanced. So my right answer is going to be 3 Na2CO3 plus 2 FeNO3 3, and that's going to yield our ion compound Fe2CO3 3 plus 6 NaNO3. Now the equilibrium expression is what our second answer. Now remember, this is a solid, so this is going to this will not be involved in equilibrium expression. So what we have is we got NaNO3, that's raised to the 6, over Na2CO3, that's raised to the cubed, times FeNO3 3, and that is raised to the 2nd. And this is the equilibrium expression for this reaction. And that's what we got here. Whoops. Yep. All right, so the next question is that we're looking at determine the mass of sugar if we've got 3 liters of saturated solution of iced tea. Iced tea is made mostly of water. So what we're going to do is I'm going to come back to my, all right, let's see the solubility of sugar. Of sugar and water. All right. All right, let's pick this one. As we're looking at this, and at room temperature. We're going to be at room temperature, 203.9 per 100 mils of water. So the solubility, if we move over here, 203.9 grams per, stop that. Per 100 mils of water. I come back here. Let's go back to that. Let me get rid of that. I want to know how. We got 3 liters. So how much sugar's in there? So concentration, 203 grams, 0.9 grams per 100 milliliters. And then we're going to take that as 1,000 milliliters per 1 liter. And then we're going to take 3 liters. Now we're doing this is dimensional analysis. The milliliters will cancel, liters will cancel, and what we have left is our concentration, is the mass of our substance, which is sugar. Let me get back to my calculator. 203.9 times 1,000 divided by 100, then times 3, and the number you should get is going to be 6,117, and that's going to be grams of sugar. That is a lot of sugar in that iced tea. Also, we got 3 liters, so you're drinking a lot of it too. So that's how you calculate those type of problems. And remember, we're looking at just dissolution or dissolving of sugar, which does not break apart. So usually you're going to have this type of reaction. Sometimes the solubility is expressed as moles per liter, and you just do the same thing. You multiply by liters to get moles, and then you multiply by the molecular weight. So let's go back to here, add a new slide. So what we have is we're going to have, say, some unknown compound has a solubility of 3 moles per liter. And the molecular weight of this compound is 100 grams. Let's make this easy. So you take 3 moles times liter, you multiply, say, about 2 liters. I'm pulling this number out of the air. Then you times 100 grams, and you're going to 100 grams per mole. Moles cancel, liters cancel, and you end up with 600 grams of the compound being dissolved in this. Guys, this is not that bad. This is just simple arithmetic. What it is trying to figure out what goes to where, and all I'm doing is making sure I can cancel my units to get the answer I want. New slide. Because as we go down, we got a couple more slides we need to go through. Determine the number of ions present in a saturated solution of silver phosphate and then silver chloride. So let's look at first. So what we have is, this is what the KSP comes in. Solubility product. So we got silver phosphate, which is Ag3PO4. Now that's our compound. So that's going to be in water, and it's going to dissociate to 3Ag plus PO4, 3 minus. So that's the reaction we're looking for. So the KSP expression is going to be Ag positive, and that's going to be cubed times concentration of PO4, 3 minus. Now, what we want to know is, what are these concentrations? So as we might need one more step, the KSP value is what we need to look for. And again, you go to we go up here, KSP of silver phosphate, and there we go. And this looks like 1.8 times 10 to the minus 5. Nope, whoops, wrong. Up here, here we go. Looking at the wrong thing. Make sure you look at the right number. 8.9 times 10 to the minus 17. So let's come here as 8.9 times 10 to the minus 17. All right, let's go ahead and. So this is what we need. So let me get to a new slide. So here's a silver phosphate. Well, I'm rewriting this. And this is what I want to see on the test. So we're going to have, we got 0 of this, 0 of this. We've got a whole bunch of this, but we don't care because it's a solid. So we're going to minus some of this coming out. We're going to have 3x here and x here because of this molar ratio. Again, we don't care about that. So this is initial, this is the change. At equilibrium, again, we don't care about this because it's a solid. It has nothing to do with our equilibrium expression, but we've got 3x and x. Now, our KSP, our equilibrium expression, is going to be equal to silver cubed plus concentration of times concentration of phosphate. Now, that's going. So we put in these values for the concentration. We're going to have quantity 3x, and that's going to be cubed times x. Phosphates is x. This is going to be 3x, and the KSP again is going to be this 8.9 times 10 to the minus 17. That number is going to equal 3 times 3 is 9. That's going to be 27x cubed times x, and that's going to be 27 times x to the fourth. Now this is where we've got to calculate. We're going to take the fourth root of this number. So we're going to take the fourth root of 8.9 times 10 to the minus 17. All right, so let me open my calculator again. So you get 8.9 raised to the minus 17. And you're going to divide that by 27 first. So take this number, divide by 27 first, then take the cube root, or the fourth root, and x is going to be 4.26 times 10 to the minus fifth. All right, so let's go to another slide, and you can see all my work is up here. So if x is equal to 4.26 times 10 to the minus 5, and that's going to be moles per liter. That's going to equal the concentration of phosphate. I'll get better with this, guys, I promise. That's equal to 4.26 times 10 to the fifth minus 5. And then the concentration of silver is equal to 3x. So you multiply that number by 3. And that's going to give me 0.000128, or 1.28 times 10 to the minus fourth molar. And that's how you solve it.